Okay, this is going to be lesson 9.1, part 2, and we're going to start with rationalizing the denominator. When a radical is in the denominator of a fraction, you can multiply the fraction by an appropriate form of 1 to eliminate the radical from the denominator. This process is called rationalizing the denominator. So basically, whenever you see something that needs to be simplified and the denominator is not able to be simplified because there are no perfect square factors underneath the radical symbol, you know that you have to rationalize the denominator. So an example would be the square root of 5 over the square root of 3n. So we are going to multiply top and bottom by the square root of 3n. This will allow us to simplify then and get the square root of 15n over 3n, and this example is in your book. The same thing would be true for the cube roots, although we won't be really touching on cube roots much in this lesson. But in this case, we'll look for the cube root of 3 because that will make it a perfect cube in the denominator. So that's where it's a little bit different. For the square roots, we definitely want to somehow have that number squared, but in a cube root, we're just looking for the next perfect cube. So remember that what you're multiplying by, and the reason that this is allowed, is because it's a fancy form of 1. The square root of 3n over the square root of 3n is equal to 1, and everything that you're going to be multiplying by will be the same thing in the numerator and the denominator, which will allow us to keep the math correct. So let's try some of these. So again, what would you pick as your fancy form of 1 for number 13? We would want to multiply by the square root of 5 over the square root of 5. And so then 1 times the square root of 5 is the square root of 5. When you take the square root of 5 times the square root of 5, you get the square root of 25. So the denominator then finally simplifies to 5, and now we have a rational number in the denominator. For number 14, we will multiply by the square root of 3 over the square root of 3. So we have the square root of 10 times the square root of 3, or we could write it as the square root of 30. And again, square root of 3 times the square root of 3, that's the square root of 9. That simplifies to 3. For number 15, you will multiply by the square root of 2x over the square root of 2x. So note that the 7 is not under a radical symbol. So 7 times the square root of 2x over, and when you get this, you'll have, when you multiply them together, you get 4x squared. So really, basically, what comes out when you multiply it times itself is just what is the radicand, the number under the radical symbol. For 16, so you can see this as the square root of 2y squared, okay, and you have the square root of 3. So what we're going to multiply by is the square root of 3 over the square root of 3. So when you simplify the top, this 2 times 3 will be 6y squared over 3, but the top can be simplified a little further because y squared is a perfect square, so we can get y square root of 6 over 3. Okay, so these are all of the solutions. Just to distinguish them. Okay. Next up is the concept of conjugates. So when you have two binomials, a square root of b plus c square root of d and a square root of b minus c square root of d, and they're all rational numbers, they're called conjugates, and we can use them to simplify the radical expressions that contain a sum or difference involving square roots in the denominator. And this concept kind of goes back to the difference of two squares, and we were able to see the patterns. So what'll then happen is you'll use the conjugate to get a squared minus b squared in the denominator, okay? And by a and b, I mean the first term in the binomial and the second term in the binomial. So here's an example. The conjugate to 2 minus the square root of 3 is 2 plus the square root of 3. So you'll multiply by, again, a form of 1, 2 plus the square root of 3. So using the distributive property, but we want to kind of hold off on that. Remember I said don't distribute until the end in case there's something else that can be simplified. 7 times 2 plus the square root of 3. And then the pattern of the difference of two squares. And here's where we see the difference of two squares. The sum and difference pattern right here. if you can remember from when we were factoring and foiling and all that fun stuff, we got a pattern here that is in the form of the first term squared minus the second term squared. So we don't actually have to multiply the 2 times the 2 and then the 2 times the square root of 3 and then the negative 3 square root of 3 times 2 because the middle terms cancel out. But when you take 2 squared, you get 4 right here. Okay? So this simplifies to 4 minus 3, and they've already simplified it to the denominator of 1. So 14 plus 7 square root of 3. So we can go ahead and distribute 7 times 2 and 7 times the square root of 3. And since it's over 1, the final answer is simply whatever the numerator is. In this case, 14 plus 7 square root of 3. So again, this is the pattern that we recall, hopefully you do, from when we were working on our factoring unit. So let's give some of these a try. So in this case, we have the conjugate 1 minus the square root of 3. Okay, so 1 minus the square root of 3. So we would simplify the top, and then the bottom will be a squared minus square root of 3 squared. 8 times, again I'm leaving this for a reason, because in the bottom we're going to get 1 minus 3, which is going to be a negative 2. And this 8 and the negative 2 can be simplified, so that's why, since I didn't distribute, I'll have less work to do in the end over the negative 2. So negative 2 goes into itself once and goes into 8 negative 4 times. So now I will distribute a negative 4, and I will get negative 4 plus 4 square root of 3 as my final answer. Okay, because I've taken a negative 4 times the 1, and I've taken a negative 4 times a negative square root of 3. Okay, in the next one, the conjugate will be the square root of 5 plus 2. The square root of 5 plus 2. So we'll take the square root of 13 times the square root of 5. Maybe I'll write that like that. And then, because it's like we're distributing that, okay. And then we're going to take, well, maybe what I'll do first for you is leave it out like we did the others. So the square root of 13 times the square root of 5 plus 2. Okay, just until we can see if there's anything that can be simplified. And then in the denominator, I will have the square root of 5 squared minus 2 squared. So square root of 13 over 5 minus 2 . Except for this isn't 2. Remember, it was 2 squared, so it's actually 4. So then we'll have, and then I'll go ahead and distribute. So I'll have the square root of 13 times the square root of 5. And then I'll have plus 2 square root of 13. And all of that, when you take 5 minus 4, you'll get 1. So I can multiply the 13 times the 5, and I get 65, and there's nothing I can break that into to simplify it, but I would look to see if there were. So the square root of 65 plus 2 square root of 13 is my final answer. All right, for the next one, my conjugate is the square root of 2 minus the square root of 7. Okay, so I will get 12 times square root of 2 minus the square root of 7. I will get the square root of 2 squared minus square root of 7 squared. So if I distribute, I get 12 square root of 2 minus 12 square root of 7 all over, and then I'll have the square root of 2 squared, which is 2, and the square root of 7 squared, which is 7. So it's going to be over negative 5, so the whole thing will be negative then. Negative 12 square root of 2 minus 12 square root of 7 all over 5. Okay, so this is just going to show you a real-life problem. This is right out of the book. And basically, it's just going to be, you know, how far can you see when your eye level is 5 feet above water, so you substitute in 5 for h, because h is the feet above water. And then you can actually multiply it down, and then instead of just simplifying it as the square root of 30 over 2, go ahead and divide it out. Like literally take the square root of 30 and then divide that by 2 to get approximately 2.74 miles. So there is a reason and a time when we actually do simplify these down to decimal numbers, when it would make a little bit more sense to tell us the distance. Another example, and this is kind of fun, is using proportions with the golden ratio. So we've talked about the golden ratio before, and it's kind of a mathematical proportion. And it is 1 plus the square root of 5 to 2, and that is the length to the width of a golden rectangle. So if you use that in a proportion, you can solve for a missing side length. In this case, they're solving for the height of the Parthenon in Greece. And so you can follow the work, you can pause the video, follow the work, and kind of look and see what they did. They get down to the very end, and you know, the height is about 19 meters if you rounded it to the nearest meter. And then, you know, you look back and see, does it make sense? And it actually does. If you compare the two ratios together, you get approximately the same decimal answer. So we're going to use that information to help us. So since the golden ratio is length to width, and we know that it is the 1 plus the square root of 5, okay, to 2, and that's length to width. So length to width, and it is 1 plus the square root of 5 to 2. If I set up my proportion this way, and I do the length on top and the width on bottom, I know that the shorter side is 50 feet, and the shorter side is always, to me, equated with the width. So I will put the 1 plus the square root of 5 on top, 2 on bottom, is equal to the length over my 50 feet. So using cross multiplication, I get 2L is equal to, and then 50 times 1 plus the square root of 5. Since I know I'm going to be dividing both sides by 2 to solve for L, I didn't distribute first because it would be much easier for me to simplify this to 25. So L would be equal to 25 times the golden ratio length. And then that's going to be equal to 25 plus 25 times the square root of 5, which should give you a length of approximately, maybe I should change it to an approximately, 81 feet. So double check that you can get that math to work out when you're multiplying and approximate it to 81 feet. Okay, the next big idea is just performing operations. So when you want to add or subtract, you can only do so if they are like radicals. They have to have the same index. Okay? All right, so you can add and subtract like radicals the same way you combine like terms. So, looking at the example from your book, you have the square root of 5 square root of 7 plus the square root of 11 minus 8 square root of 7, and you can see the like terms right here. 5 square root of 7 and the negative 8 square root of 7, and then your square root of 11 is its own term. So you can combine the terms outside the 5 minus the 8 and simplify that down to a negative 3. For part B, don't let the square root of 20 fool you, because it can be simplified to square root of 4 times the square root of 5, or 2 square root of 5, and then we actually do have some like terms. All right, so again, pay attention to simplifying radicals so that you can find like terms. In multiplying, you'll just do the distributive property. So the square root of 5 times the square root of 3 minus the square root of 5 times the square root of 75. You can combine them, multiply them, and then look for some perfect square factors to simplify. So let's try these. In this case, we have 3 square root of 2. We have a negative square root of 6, looking at each term individually, and a positive 10 square root of 2. So these two have the same radical. This one does not. So I can combine 3 and the 10 just like I would a coefficient in a variable expression. So 3 plus 10 is 13 square root of 2, and then minus the square root of 6. Okay. In this case, 4 square root of 7 minus 6 square root of 63, I can see that my 63 can be broken up. Because 63 is actually the square root of 9 times 7, and I know that the square root of 9 is 3. So I will have 4 square root of 7, and then 6 times 3, or 18 square root of 7, as a simplified form. And then 4 minus 18 is negative 14, and I'm left with the square root of 7. If I'm going to distribute down here, so I don't want to worry about combining like terms or trying to add things or even break 32 up into anything. I want to distribute. So I will have 8 times the square root of 3 times 2, or 8 times the square root of 6. Then I have 7 times 3 times 32, or 7 times the square root of 96. And since I already see the square root of 6 over here, I'm going to look to see if I have a 6 as a factor of 96, and I do. So I can simplify, right, because this is going to be 7 times 16 times 6. So now I know I'm pulling out a factor of 4 because the square root of 16 is 4. So 7 times 4 changes to 28. So 8 square root of 6 plus 28 square root of 6 can be added or combined to be 36 square root of 6. In this case, we're going to be doing some, so we have a 2 square root of 5 minus 4 and 2 square root of 5 minus 4. So the 2 square root of 5 becomes squared, right? So we'll have like this, 2 square root of 5 squared, which is going to be 2 squared times square root of 5 squared, or 4 times 5, which is 20. That's the first term. The outer term will be a negative 4 times 2, or so a negative 8 square root of 5. The inner terms will be a negative 8 square root of 5, and the last term will be positive 16. So we'll have 20 plus 16, which is 36, okay, and then a negative 8 square root of 5 plus a negative 8 square root of 5 will be a negative 16 square root of 5.